We are ready to start the last session of today, and we will hear now from Simone Rijavec from the University of Oxford about Page-Wooters construction in the context of Oxford. The stage is yours.
Hi everyone. So yeah, I'm going to talk to you about some results of the Page-Wooters construction and some variations. So yeah, I'll start, since someone mentioned it yesterday, I will start with some background and some summarizing the Page-Wooters construction. So when you don't know what it is, I'll do it here. Then I'll show you how to formulate the construction in the Heisenberg picture, and how to extend the construction to include the mixed state of the universe and also system clock interactions. I'm going to go briefly over the background. So in physics there is this problem of time, it's so-called problem of time, which is sort of an umbrella term for a variety of issues related to time. I'm not going to go into this. I'm just going to say that a potential solution was proposed by Page-Wooters in 1983. And Page-Wooters start from a stationary state of a universe. So a universe in which time, the background time parameter, has been effectively removed. They subdivide the universe into two subsystems. One is a system which we're interested in, and the other one acts as a clock for the first one. And they show how you can recover usual Schrödinger evolution on the system side in a relational way, so it's relative to the clock. So I have three questions. The first question that I want to highlight about this construction is, can we formulate it in the Heisenberg picture? This is for completeness, not only for completeness, because we can argue that in the Heisenberg picture we can get some more local description of some processes. And it's not trivial if you look at the state vector of the universe, because the state vector of the universe is stationary, so we don't have that limiter that we use to switch to Schrödinger and Heisenberg picture. But anyway, this is more like a curiosity. But then led me on to asking, can we do the same for mixed state of the universe, or can we consider mixed state of the universe? And what is the difference in the construction if you use mixed state of the universe? And finally, what happens when you introduce system clock interactions? There are some funny effects that happen, and I'm going to show you some of them. But related, so the joint study of these three problems led me to the to analyzing this question. So is the energy eigenvalue of the universe an observable quantity? Because in the usual model, by Page-Wooters, it's not. But I'll show you that the system clock interaction between changes. Another question that sometimes is not clear in the literature maybe is what is the role of entanglement in the construction? And I'm going to try to explain a bit more of that. So back to the Page-Wooters model. So the basic assumptions of the models are these three. So we start from a universe which is in a state of psi, which is an ideal state of the Hamiltonian of a universe. This is the Wheeler-DeWitt equation, or a variation of the Wheeler-DeWitt equation, because here we allow for any energy eigenvalue. So I'm just going to allow for any energy eigenvalue, and I'm going to show you that it doesn't change much, the conclusion. Second point, the second assumption is that the universe is made up of two systems. So here we have a simple model. One is a system in which we're interested. The other one acts as a clock for the first one. And there's no interaction between the two systems. So the Hamiltonian of the universe, curly H, is just the sum of the Hamiltonian of the system plus the Hamiltonian of the clock. Third assumption is that the clock is an ideal clock. So there's this simple algebra. So it's the time operator T conjugate to its Hamiltonian. And this makes everything simpler, but it can be generalized, this third assumption. Great, so usually how it works is that you start from, you can start by writing the state of the universe in this way. So you just expand the state of the universe in this way, you just insert the composition of an identity in terms of the eigenstates, T, the eigenstates of the Q operator of the clock. You can do that always. You just assume some sort of normalization on the system side, which in this case is independent of T. And then you apply, here in the first quality, you apply the constraint in this unitary form. And this is the stationary constraint, so these unitary acting on this gives you just a phase. And the second equality comes from the algebra of the clock. And so by equating 1 and 2, we find that on the system side we have this relation, so the state of the system obey this relation. So if you interpret this psi of t as the state of a system relative to a clock being in the state t, so basically having measured the state of the system when the clock is in the state t, then we see that the state of the system evolves in the usual Schrodinger way, so the usual Schrodinger evolution. And I want to point out that there's this eigenvalue of the state of the universe psi here that appears, but it only appears as a phase, so it's not an observable quantity. Another thing I want to mention is that, as you can see from equation 1, we have a non-trivial time evolution in the sense that the state of the system has at least 2 different states at 2 different times. If only the state of the universe is entangled, so there's entanglement between system and clock. But this, entanglement, on the kinematic Hilbert space. And from now on, I'm just going to refer to the kinematic Hilbert space for those of you, you know what I'm talking about. Okay, great. So can we do the same for mixed states? Yes. The constraint just becomes this one, so it's a generic constraint becomes this one. So R is the state of the universe. It must commute to the Hamiltonian of the universe. We can define the relative state of the system. So the state of the system relative to the clock being a state in state t in this way, where phi of t here is just a projection of the t eigenstates of the clock. And again, we do a similar procedure and we find that the state of the system evolves in the usual Schrodinger evolution. And again, we don't see any eigenvalue appearing here. So R here can be one eigenvalue, one eigenstate of the Hamiltonian universe. It can be a statistical mixture of different eigenstates of the Hamiltonian universe, and we will not notice any difference in this scenario. Great. Okay, so how can we go to the Heisenberg picture? There are some words doing that. I'm not going to get into details about differences between these words, but I'm going to show you one way I found, which is quite simple, and starts by a simple observation that we can always write the state of the universe in this way. So this is just what we see now to now. So the system is going to evolve in the usual Schrodinger way. But now we can take this unitary out of the integral sign by upgrading t to the t operator. And here TL is this timeline state vector, which is just a superposition of all time instances of the clock. So now what do we do? We just transform unitary observables with this unitary U. And basically we define the Heisenberg picture observable of the system in this way. And now notice that they are supporting the full inverse space of the universe. And we define that the Heisenberg state in the following way. And crucially, the Heisenberg state is several state. So according to what we've seen before, we can code no time evolution. So if you were to do the Schrodinger picture construction, reconstruction with this state, you will see that the system doesn't evolve. So the relational dynamics of the system is trivial. So we just did a unitary change of base. I'm just going to show you quickly how some important observables change in the other picture. Crucially, the Hamiltonian of the system is invariant and the time operator is invariant as well. And the Hamiltonian constraint, so the Hamiltonian of the universe, becomes the Hamiltonian of the clock. And this is this word upon means that the constraint has been trivialized. Okay, so how do we recover the usual Heisenberg evolution of the observable? We define relative observables, so we just project our Heisenberg picture observables with a projector on the t eigenstate of the clock. We can even, in some sense, trace out the clock from these observables, and we find that the usual Heisenberg evolution for the observables of the system. So we have found one way to go from the Schrodinger picture to the Heisenberg picture. Is this way unique? I'm not going to go too much into this, but yes, apart from if we require these things, so require that the Heisenberg state doesn't encode any time evolution, then this unitary is unique up to local unitaries. Yeah, by the way, the same way can be done with mixed states of the universe. So I do here the same with mixed states of the universe. This is a general way of writing a stationary mixed state of the universe. For this specific Hamiltonian, the state has this form. And again, we see that we have this unitary that you can take out of the integral sign. And so we do the same thing as before. And now the Heisenberg state of the universe is going to be this state, which is a so-called quantum classical state. But importantly, it's again a separable state between system and clock. So we have moved the correlations, the entanglement from, or the correlation, I must say, between the state and the observables. The observables again are defined this way. And again, we can trace out the clock and find the usual Heisenberg evolution for the relative observables of the system. The important thing I want to mention is that, okay, again, this Heisenberg state of the universe is such that we use the linear clock, which implies that there's no time evolution encoded in the state. So if you do this, showing a picture construction with this state, we don't get any non-trivial time evolution, or relative time evolution for the system. Again, this transformation is unique apart from local unit transformation. But crucially, and this leads me to another point, is the set of states that commute with the Hamiltonian of the clock is smaller than the set of all separable states, separable within the system clock, which points to the fact that there might be another separable state which doesn't commute with the Hamiltonian of the clock, but encodes like some time evolution. That is the case. So now, forgetting about Heisenberg picture, even if you work in the Schrödinger picture, if I give you this sort of state, this is a separable state between system and clock, but it encodes the usual time evolution on the system side. So if you do the construction, usual construction with this state, you recover the usual Schrödinger evolution on the system side. What does it mean? It means that contrary to what sometimes is believed, entanglement is not really necessary in the model, not even at the kinematical level, not even on the kinematic universe space. And it's an interesting fact. There might be connection here with the classical relational models of time, but I'm not an expert about that, so I'm not sure. But it's good to point this out. So we don't really need entanglement as long as we allow for mixed state of the universe. And crucially, this is a fact that will become useful later, to construct such kind of state, we need to allow multiple energy eigenstates of the Hamiltonian of the universe. And this will become important later. But again, just to make the point clear. So they found a way to go from the Schrödinger picture to the Heisenberg picture. It's just, this transformation just moves the correlations between the state of the universe to the observables. Of course, we didn't make, so entanglement doesn't disappear in the Heisenberg picture. We just move it to observables. So, and as always, entanglement is not only a property of the state, but also the subalgebras we are considering. So in the Heisenberg picture, we have modified the subalgebra of system and clock. So that's why we're still entanglement. Oh yeah, and a good Heisenberg state, as we've seen, must not encode any time evolution. So it means that if you do the construction, the Schrödinger picture construction with this Heisenberg state, we don't get any non-trivial evolution out of it. Now, focusing on the Schrödinger picture, we've seen also two things. One, that for pure states, we have non-trivial time evolutions, if and only if the state of a universe is entangled between system and clock on the kinematic universe space. And for mixed states, we've seen that even separable states of the universe can lead to non-trivial time evolutions. But the catch again, the thing that we have to remember is that we need to allow multiple energetic states of the Hamiltonian of the universe. Great. So how do these things change in the presence of system-clock interactions? Well, let me consider some interacting models. So we had an interaction term between system and clock, V. The study of the general interaction is quite complicated. There's a lot of funny things that happen. I'm going to restrict the class of interactions with three constraints. We can discuss more about this maybe later. One is the way of imposing energy conservation in some sense. The second one excludes, as we will see later, but the effective dynamics of the system as a time-dependent Hamiltonian. So we're just focusing on time-independent Hamiltonians for a system. And the third one is that we want V of order 1 in the Hamiltonian of the clock. So the equations of motion of the system are just going to contain first-order time derivatives. And by the way, these constraints exclude some types of non-unitarity that have been shown in the literature. And so this should be an acceptable constraint, and will be like some nice properties for the dynamics of the system. Then what we have left after applying this constraint is something of this form, where X is an operator that commutes with the Hamiltonian of the system, and it's an emission. I'm going to consider the simplest version, which is just the Hamiltonian of the clock times the Hamiltonian of the system, with a coupling factor, lambda. And this is sort of, if you could plug in this value for the coupling constant, it's sort of a Newtonian potential with some post-Newtonian correction in some sense. So let's solve the model with this interaction. So you can find it here how to do that. Basically, the solution is this one. So we see that the system, instead of evolving with its own bare Hamiltonian, H, will evolve with an effective Hamiltonian, which for the potential that we've seen before, with the interaction we've seen before, is of this form. So there's a funny term at the denominator here. Wait, sorry, effectively the dynamics of the system changes. We have an effective Hamiltonian. Oh, by the way, I'm going to mention that again, we can recover the Esner picture by taking out this unitary from the integral and then making it applying it on the observables. And by the way, just briefly, these are how some important observables transform in the Esner picture. And I want you to notice that the constraints of the Hamiltonian of the universe is not trivialized anymore. So now, if we take the Esner picture Hamiltonian of the universe, it will also take this V. So it's not trivialized in the sense of the work of Horn and others. But crucially, now we see this thing that if you consider different energy eigenstates of the universe, the effective Hamiltonian changes in this way. And now here, epsilon is no longer a trivial energy shift, but it gives rise to an important difference. So, for example, for small coupling factors, but here should be much greater than one. You can expect like this. And for example, if you take a universe in an energy eigenstate with eigenvalue epsilon, and another universe with an energy value epsilon prime, then their dynamics is substantially different. But I leave open the question of whether this is an observable thing from the point of view of the system. It's an interesting question. Can we do the same for mixed states? Yes, we can find a solution for mixed states. And here where things become a bit more interesting, because now if you allow for multiple eigenvalues of the Hamiltonian of a universe, so if you have, for example, a statistical mixture of multiple eigenstates of the Hamiltonian of the universe, the evolution, so the dynamics of the system relative to the clock, is no longer a unitary evolution. So we have some non-unitarity effects arising. For example, if at the time 0 all these rho k are the same, the effective evolution of the system will be given by this CPTP map with these Krauss operators. And so, in some sense, we have lost unitarity. And this has happened because of interactions. Because in the original Page-Wooters model, if you have statistical mixture of different energy eigenstates, it doesn't matter. You can't observe that. But here, with interactions, we see an effect, a complete effect, which is non-unitarity in the system dynamics. By the way, in this context, the Azure picture is no longer obtaining the unit transformation. We need to act with the adjoint map and the observables. But I'm not going to go into this. Another interesting consequence of this is that if you want to consider only unitary evolution for the systems, then so we have to exclude the different energy eigenstate of the universe, which means, as we've seen before, that we have only to consider entangled states of the universe. We can't get away anymore with the separable state of the universe. And it's interesting. So, in some sense, interaction restored the role of entanglement in the construction. So let's go to let's put some numbers in and see when this non-unitary effect becomes important. I'm gonna consider a very simple model. So we have a qubit, so a two-level system interacting with an ideal clock, and I'm gonna add a mass term, so less energy term, to spice things up. So effectively, what we have is a massive Schrödinger cat interacting with a clock. And we can solve this system, this model, and we can find the effective Hamiltonian of the system, of the qubit, and there's going to be these two terms appearing. Doesn't matter much the details. The first one is unobservable because it's an identity, so that's going to give you a phase. And the second one basically multiplies the bare Hamiltonian of the system by this factor, so it's a scaling factor. So it changes how fast the qubit rotates. And so let's assume that the universe is in a statistical mixture of two different eigenstates, one with eigenvalue 0 and the other one with eigenvalue epsilon. The effective dynamics of the system is going to be given by this expression. We plug in the numbers from before, and we find that this term, so the density, so the state of the system is going to go to the maximum unique state after this characteristic time here. So, and this is peak non-unitary in the sense that we started from state 0, and we end up in the maximum unique state after this characteristic time. A more significant quantity is the number of full rotations that the qubit can do before it gets to the maximum unique state. And as you can see, depends here which quantities are important for this phenomenon. So the coupling constant, so the strength of interaction between system and clock, and the size of the superposition, so the difference between the energy values. As an example, we put a Newtonian potential. We assume that the energy gap is of the order of the mc squared within the mass of the qubit, and we find that this parameter is equal to the distance between system and clock divided by the Schwarzschild radius of the system. So, which shows that it's quite a weak effect for gravitational interactions, but it may not be that weak for other kinds of interactions in other systems. So we can use this to study other kind of effects. Another funny thing that I want to show you is we set the parameters for the effective Hamiltonian of the system that I showed you before, and we plot them. So I plot them here as a function of the coupling constant. Here in this graph, big values of lambda mean no interaction, so ideal case where system and clock are not interacting. Small values mean maximum, like strong interaction, here is the maximum. So phi again is an observable phase, so we don't care about this. We care about omega, which is the speed of rotation, so how fast the qubit is rotating. And as we see, so if you go from minus plus infinity, it's going to tend to 1 omega, so the qubit above is bare Hamiltonian. But now let's come from negative values of lambda, and let's increase the strength of interaction between system and clock. And we see that the qubit starts rotating faster and faster and faster. And there is this value where this goes to infinity. So it's sort of like, so time, like the time for the qubit in some sense changes. But the funny thing is that when we cross this value, this critical value of lambda, then the qubit rotates in the other direction. So it looks like the qubit is rotating in the other direction with respect to the case of like no system clock interaction. So in some sense there is this time inversion. So it rotates in one way before this critical value and rotates the other way after this critical value. In this small region here, and again there's another critical value here, and then the system starts rotating again in the right direction. If you plug in some numbers and the internal potential, you find that these critical values are around half the Schwarzschild radius of the system in a small region. Usually this is quite small, so this is a small region around half the Schwarzschild radius. And this half factor we discussed before with some other people might be, but it's not like a fully relativistic approach to the problem, and considering other things, we could get actually the Schwarzschild radius of the system. So it's an interesting attack that happens potentially on the horizon of the qubit black hole. But I'm not an expert in this, so I'm going to leave this open. So yeah, coming to the conclusions, we've seen that the other picture, a very formulation of the Page-Wooters construction can be seen as a transfer of correlation, of system clock correlation between the observables and the state and observables. This transformation works for mixed state of the universe and with some types of system clock interactions. In the case of no system clock interaction, which is the usual case considered by Page-Wooters, it doesn't matter which energy value we're considering, energy value of the universe we're considering. And entanglement is not strictly necessary for the construction to work. But when we add system clock interactions, then we see that different energy states lead to different dynamics, which may or may not be observable. But multiple energy states, so if you have a statistical picture of multiple energy states, then we have non-unitary dynamics for the system. And here, just questioning. So maybe like the constraint should be applied in the following form, maybe, so precisely zero and yeah, so that's a question. But so maybe yeah. Another thing we've seen that with system clock interactions, unitarity. So if you want to preserve unitarity, then we need entanglement in the state of the universe. And finally, yeah, we see this funny time inversion effect for strong coupling between system and clock, which happen at sort of relativistic scales. Yeah, and that's all. You can find these results here. Yeah, and thank you for your attention.
I think we have time for one or two questions, but I saw Max first.
Yeah, thanks, super interesting. I have like two technical questions per page, but maybe we'll talk about those later. A conceptual one then for now. Is there any way to, or what's your interpretation of the meaning of putting the universe in a superposition or a classical mixture of energy eigenstates?
Yeah. So first of all, we could apply this model to any stationary closed system. So it doesn't have to be the universe. So we might, for some reason, consider a sub-region of the universe, which we know it's stationary, it's a closed system, and we could apply the same construction to that. So it's good to have this possibility to analyze mixed state of the universe. I tend to prefer pure state of the universe, but I don't know, because in some papers were mentioned that some mixed state of the universe might be also fundamental, but I'm not really an expert in this. But it's good to have the possibility of analyzing also mixed state of the universe, especially because we can apply this model in the lab, make a little closed system, and put it in a stationary state, and draw some conclusions.
I was interested to hear you ask whether there's a classical analog of these things, and I think the answer is yes, and I think you agree. In fact, it was discovered by Poincaré a long time ago. So if you take two simple harmonic oscillators perfectly classically, and prepare the system in a state of different energy for both, then we know the orbits necessarily lie in a torus. So I don't need time, I just take a section through one part of the torus to define a plot for the other one. It's the exact classical analog of what Page-Wooters are doing. And so that suggests straight away the connection is between the microeconomical ensemble and the canonical ensemble, if you want to consider mixed states distributions like that. You said, I don't know if you've thought about this or you would agree with it. It's something that's occurred to me over the years, but it seems to me that basically it's a quantum version of Poincare section.
Yeah, I'm not aware of this work, so yeah, thank you for your thought.
Okay, maybe actually, since you already asked your question, then maybe we can like to discuss with Simone later, so let's